Hi, everybody. This is Dr. Collins again. So, today we are going to talk about how we actually calculate correlations. Today is going to be a little bit more math intensive, but I know you'll all be fine. So just again to remind you, we have our Internet Explorer versus murder rate chart up here. So, you can kind of see that in this case, right, is it a negative or is it a positive correlation? A little bit of a trick, right? So they're both trending downward together. So the point is they're trending in the same direction together. Therefore, it is a positive correlation. Okay. Now, obviously, this is a clear case of correlation and causation not being the same thing. Okay. So just to give you a quick look at that. Now, again, remind you of the agenda. Last time we went through correlations, what you may already know. We talked about how to think graphically about these correlations, as well as positive and negative or direct and indirect correlations. So today we're going to, as I said, talk about calculating correlation coefficients, right? How do we actually calculate the thing that we want, right? Which is that numerical correlation. So we'll also talk about how we interpret these correlations. What is a good correlation? What's a strong correlation? Okay, so stay tuned. Here we go. Now, in calculating correlations, right, some of the first things that we need to do, we start by evaluating what's known as the covariance of two variables. Literally, how well do they covary together? So remember Kelstedt and Witten's third causal hurdle, do the variables covary, right? Do they vary together? Okay, so that's what covariance is. It looks to see to what extent they covary together. It's not the same thing as correlation, okay, but it's a good jumping off point. Now, your textbook doesn't talk much about covariance at all, right? They give you sort of a straightforward, here's your formula for correlations. I'm taking a little bit of a different route and showing you another way to calculate it. Now, mathematically, it's the same thing. It's the exact same way to calculate it, okay? And I'll actually demonstrate that to you in our demo. But for now, right, I'm going to show you this way of calculating correlations because I think it makes a little more sense. Okay, so how do we evaluate covariance? Right. Well, let's revisit our graph that we worked on last time, right? So we have quarterly presidential approval ratings and quarterly unemployment. That's on the x-axis. Presidential approval ratings are on the y-axis. Now, if you'll notice, I've actually added two additional things on here, right? I have added a line here and a line there, right? So the line here is actually the line for the mean of unemployment in this data set. Okay, so if you look across this x-axis, right, I drew a vertical line here saying the mean of unemployment is just above 6% in this whole data set from 1978 to 2006. The same is true on the y-axis here. Okay, so I've drawn a mean for presidential approval. You can see there it's about 52, 53. Okay, so why have I done that? Well, in order to understand covariance, you can get a good look at it graphically, right? So here we have our graph. I've drawn these two lines because it'll give you some sense of, generally speaking, what covariance is. Okay, so look in that top left quadrant. All right, you'll see there I've added a negative sign. Okay, why is that? Well, any observation in this quadrant is above the mean presidential approval, but below the mean unemployment. Okay, so positive, negative, that's a negative. Okay, you'll notice here in the upper right quadrant, this is positive. Why? Because both are above the mean. It's above the mean of unemployment as well as above the mean of presidential approval. So obviously continuing this trend, we have two things that are both below the mean of unemployment and presidential approval. So that's also positive, negative, and a negative is a positive. And last but certainly not least, right, we see those things that are above the mean unemployment but below the mean presidential approval. Now, generally speaking, if you sat down and you counted out all of the individual dots in each quadrant, right, and you added all the positives together and all the negatives together, whichever one has more dots, that's going to be your covariance. And it's also going to be your correlation, right? So if you have more dots in this quadrant and this quadrant, you have more observations here and here, you're going to get a negative correlation. If you have more here and here, you're going to get a positive correlation. Okay, so I'm not going to give you time to sit there and count all these dots. You theoretically could if you want, but there are slightly more dots in the negatives, right? And as I said last time, right, a properly fit line would probably look something like that. Okay, so evaluating covariance. There is your equation for covariance. Okay, so take a look at it. Right, so we see here the covariance of x and y, that's all the comma means, right, is equal to the sum of this. So what is this? Well, let's walk through it. Right, we know that xi is an individual observation for x, yi is an individual observation for y. Right, so you can imagine that in the case of our data from the previous slide, you could imagine that each one of these is an individual quarter. Right, so a quarter of unemployment. So what is the quarterly unemployment rate at that particular quarter? What is the quarterly presidential approval in that quarter? Okay, that's all that means. And then, of course, we're familiar with this notation, x and y bar. X and y bar are the means of x and y. So what do we have here? Well, we have a deviation of x from its mean and the deviation for the observation's value of y from the mean of y. That's all it is, right? So we have how far away is it from the mean and in what direction? How far away is it from the mean on y and in what direction? You multiply those two things together, right, for each individual observation. And then we see there the sum, the summation notation. All that means is we add it up for every observation. That's all. And then we divide that. Basically, we scale it by the total number of observations, n minus 1. Okay, so we add that little penalty because that introduces a little more uncertainty. Okay, we're dividing it by a slightly smaller number. Okay, all right, so what does this mean? Well, it's the deviation from the mean for each. That's it. We're familiar with that when it comes to standard deviation in each individual variable. Now we're just looking at two variables. If they deviate in a similar direction, think about what that would mean, right? If on average, right, if something is below the mean of x and below the mean of y, they're both negative. If something is above the mean of x and above the mean of y, they're both positive. In both cases, multiplying them together, you'll get a positive numerator. Therefore, it's a positive relationship. Okay? If they deviate in opposite directions, you'll be multiplying, say, a positive if it's above the mean of x by a negative if it's below the mean of y. Or vice versa, right? Below the mean of x and above the mean of y. In which case, you have a negative times a positive. That's negative. Your relationship is going to be negative. Okay? So if you have more cases where it's below the mean on one and above the mean on the other, it's going to be a negative relationship, just like we saw graphically on the last slide. Okay? So we have a covariance. Right? All a covariance is, right, is it tells us basically on average how far away is it from each, how far away is each observation from the joint means. That's it. Okay? But covariance is affected by the scale. That is how the variables are measured. Right? So if we have unemployment, unemployment didn't have a huge range, right? It was like 2 to 10. Right? It's not a massive range. Okay? Presidential approval, a little bit bigger, right? Roughly 25 to say 65, right? Except we have those weird cases in like 2001 where it's abnormally high. Okay? But generally speaking, it's around 20 to 65, 25 to 65. All right? So what does that mean? It means you're going to get a wider variance on y, right? And you're going to get smaller deviations on x. Now imagine if you had two variables that want to scale from 0 to 1,000 or negative 1,000 to 1,000, right? You're going to get much bigger values in the covariance. So you can't really compare the covariance of two variables to the covariance of another two variables. They're not comparable, okay? Instead, we need a measure that allows us to think of a relationship without reference to the scale. That will allow us to compare relationships, right? So we can say that quarterly presidential approval and unemployment are related to one another with this value, and quarterly presidential approval and quarterly GDP growth are related to each other on this value, and we can directly compare them. Okay. Now, the correlation coefficient does this well. That's what it is. Okay, that's what a correlation coefficient is. It's basically a standard version of a covariance. That's it. Okay, it puts it into that standard score like a z-score, remember, where you divide something by the standard deviation, right? That tells you how many standard deviations away from the mean are you. That's a z-score. That's all it is. Same thing here, right? We're dividing it by something that allows it to have comparable values, right? Regardless of what the actual variables are that we're looking at. So the correlation coefficient does this well. We're going to be using the Pearson's correlation coefficient. Now, there's lots of things this goes by. We're going to focus on just calling it our correlation coefficient. It is by far the most commonly used. Okay, there are other versions of it. There are other versions of correlation coefficients, but this is the one that's going to satisfy our purposes in this class. And here it is. That's it. So Pearson's are, right, the relationship between x and y, the correlation between x and y, that's what this shows, is equal to the covariance, which we calculated on the last slide, right, which is just the sum of the product of the two deviations divided by n over 1, n minus 1 rather. And then notice what we're doing. We're dividing it by something. What are we dividing it by? Well, we're dividing it by variance. Okay, so we have the variance, which remember S is just standard deviation. S squared is variance. So we multiply the two variances of x and y together, and we take the square root. So basically what we're looking at here is shared variance or covariance divided by the combined variance of these two things. Right? How dispersed are these? And to what extent do they move in similar directions? Right? So the shared variances, to what extent do they move in similar directions? Combined variances, the overall variance, the overall dispersion of these two variables. Basically, with correlation, we're asking what share of the variance is actually shared between these two variables, right? So if two variables always move in the same direction and the same magnitude, then they're going to be perfectly correlated. 100% of the variance is shared. Okay, as one moves, the other inevitably, invariably moves in the same direction if it's positive, or the opposite direction if it's negative. Okay, if they're completely unrelated, right, then we have a zero correlation. 0% of the variance is shared. All right, so that prior equation is the more common sense one. It's this idea that you can see in the math exactly what you're doing with a correlation. Your textbook gives you another way to do it, and it's one step. Mathematically, it's identical. That's what it looks like. It's kind of a nightmare. It's why I didn't show you that one first. And mathematically, you could walk through it, and you can derive this exact equation out of the prior equation, but it's difficult, okay? Just trust me for now that these are the two equations, that they are the same, okay? Mathematically, same exact equation, right? Basically, if you inserted the correlation or the covariance measure there, and you redefined your variance by the actual way to calculate the variance, you would get this. It's less intuitive than the earlier one, but it's kind of only one step, kind of, okay? All right, so you've now seen how to do the basic calculation. How much of the total variability in these variables is shared? Again, it ranges from -1 to +1. -1 means it's perfectly correlated. 0 means it's perfectly independent or unrelated. +1 means it's perfectly positive correlated. But this raises a question. What's a good correlation? How do we know that two variables are really related? Because mathematically, we can get any values here, ranging from -1 to +1. 0.01, 0.1, 0.2. Where's our threshold for saying that two variables are in fact related to one another? Depends. Okay, it really does depend. Not so much on the scale of your variables, but right, think about that third causal hurdle. Right, if we can show that they are related, great. Let's move on to the fourth. But if we can't, maybe there's something masking their relationship that we need to account for in order to clear the fourth causal hurdle. Okay, so we can't necessarily rule out that a correlation of 0.15 is a bad correlation. Okay, because maybe once we account for other variables and we took what's known as the partial correlation, which you can see in your textbook, which I'm not going to go too much into, and I'm not going to make you know it, right? But if you did that, maybe you would see a stronger relationship between those two variables. Maybe that 0.15 would become 0.6. Okay, that would be really interesting if that happened. All right, so in the case of our data, these two variables are correlated at negative 0.305. Okay, so they share about 30.5% of their variance. All right, and they're negatively related. Okay, they have that indirect negative correlation. Okay, now interpreting these correlations, we can't say for certain that R equals negative 0.305 is a good correlation. Generally, greater than positive or negative 0.5 is considered a strong correlation. 0.3 to 0.4 is kind of a moderate relationship. Less than 0.3 is a weak or no relationship. But again, it sort of depends, right? Once we account for other variables, that correlation could increase. I'm not going to show you how to do that now because there are better ways to do that without going through the correlation. But correlation is really useful in a bivariate context with two variables. Another concern, right? Remember, we're only looking at a sample. We looked at quarterly from 1978 to 2006. That's 14 years since then that we haven't looked at, right? And theoretically, right, we don't have great data going back much earlier, but we have quarterly unemployment and presidential approval, generally speaking, right, even though it was never actually measured. Like, what was it like during George Washington, right? So what we're looking at is really just a sample of our data, right? So we know it's not zero in our sample, it's negative 0.305. But is that true in the population? Right? This is getting at that statistical inference that we're going to come back to in the next unit. Okay, so keep that in mind, right? We need some way of knowing that. So again, we might set up a null hypothesis that says that the correlation is truly zero, right? That's our assumption. Right? And then what we do is we go out and we test our current calculated correlation from our sample against that proposed null. And we try to see how likely is it that we would get this result if the true value were truly null, if the true relationship were truly zero. Okay. So we would use inferential statistics for that. Now, diving a little bit deeper before we wrap up today, how else might we examine the relationship between monthly presidential approval and unemployment? Well, graphically, how could we do it? We've already done it, right? Draw a line. Okay, that's a line. That's what we call a best fit line, in fact, as we'll see. You draw that line. Now, that line, how do we know if our line's any good? How do we know if that is the best fitting line? Well, mathematically, there is a name. Can we draw a straight line through the data points such that the distance between the points and the line is as small as possible overall? So the distance between each individual observation and the line, right? Drawing a straight line up or down. Right? Perpendicularly, actually, is what you would do. So how do you do that? Right? Well, mathematically, there is a way to do it. It's sort of a preview of what's to come. That's actually called regression. Okay? So regression is actually what we're going to come to at the end of the semester. Okay? So wrapping things up, again, we're looking at correlations right now. Correlations are pretty straightforward. All right? It's that covariance, which again is the sum of the product of the two deviations divided by the n over 1, n minus 1 rather. And then in order to calculate the correlation, you just have the covariance in the numerator, and in the denominator is the square root of the product of the two variances. That's it. Okay. Or alternatively, you can use that really long equation that we looked at from your textbook. Either one works for me. Okay. They're both relatively straightforward, I think. There's just a lot of tedium involved in it. Okay. So with that tedium set, I'm giving you the opportunity. I'm not going to grade it right now, but I'm giving you the opportunity to go ahead and try it yourself. Okay. So what is that going to look like? Well, we're in the midst of this little pandemic here, so I thought I'd collect some data on it. So As of yesterday at 4 p.m., yesterday, I'm recording this on the 22nd, so as of the 21st at 4 p.m., okay, that's Saturday the 21st at 4 p.m. These are the number of COVID-19 cases per 10,000 people in each of these jurisdictions, mostly counties, right? 7 counties plus New York City. So New York City here is defined as New York County, Brooklyn or Bronx County, Kings County, Queens County, and Richmond County, Staten Island. Okay. And I took the top 8 counties or top 8 jurisdictions, and I calculated the total number of cases they have divided by 10,000 people. Right? It's actually divided by the population divided by 10,000. Right? So we see here Westchester is really sitting up there. Right? They have fewer cases overall than the city. Right? The city has over 6,000 cases as of yesterday. Right? Westchester has about 3,000. Westchester has far fewer people than the city. Okay, so basically per capita, they have a lot more cases. They have almost double the cases of the city. Right? Nassau has actually seen a spike recently. Now these numbers are probably going to even out because we're out of tests. Okay, but generally speaking, right, you can see here, these were all the counties with at least 45 confirmed cases. Okay, now over here we have our other variable, population density. So you can imagine a hypothesis that says more dense areas are going to have more cases because people interact with each other more, people encounter other people more. More densely populated an area is, right, more people per square mile, the more densely populated an area is, the more cases they'll have. Maybe. So I want you to go ahead and try that for yourself. Okay. If you have any questions, obviously, feel free to email me. My email is at the end of these slides or at the end of this video. So go ahead and email me if you have any questions or if you want any kind of clarity on anything. Okay. I'll go ahead and leave this slide up and get rid of my face here. Okay. All right. I will see you all in the next video. Thanks.